All right. Hey, friends. It's deep.net. I think we just named it that. This is now the deep.net show.
Awesome.
And we are doing LINQ part 2. When last we left our heroes, Stephen Toub had implemented our own iterator. Let's go ahead and take a look at the code here, which was darn near as fast as the one that we shipped here. Like, we've got benchmarks, we've got our own enumerables, our own iterators, and then which one's ours and which one is the compiler, and what do we got?
So this one here is the simple iterator, the 2 or 3 line iterator that was just using yield return. This one that is effectively the exact same speed is the one that we manually implemented to show that they're basically the same thing. We were hoping that it would be exactly the same. I mentioned that it allocates a little bit less. This just has to do with how the compiler is building the state machine object. Hopefully it'll get better in the future, but regardless, it's basically the same. But we noticed that the actual LINQ implementation, it was 3 or so times faster. And you had a hypothesis for why that was, and it turned out to be the case. We highlighted how if we were to print out different the type of that we got back from the enumerable.select, that it was specializing it for different input types. And we saw how there was an array select iterator and a list select iterator and so on. And you asked, I think, as our parting shot across the bow, could we possibly do that ourselves? And the answer was yes, next time. So this is next time.
Okay, so how many different iterators, custom iterators, does .NET ship with? And did it ship with this many when LINQ first came out?
So that's a great set of questions. So first, we can actually see, so I've got source.net here. And if with the way LINQ is implemented, we try and share as much code as we possibly can. We don't want to reinvent the wheel for every iterator. So we actually have an internal base class called iterator, which is down here. And it doesn't have that much on it, but if you've watched the previous video, you'll see some familiar things. Like, you see this thread ID that I talked about that was used for the thread safety. You see a state field. We walked through all of this, right? It's just factoring that out. The current, and you see all this stuff that should look really, really familiar. There are some things, because this is a base class, that are abstract in a way. So rather than having to manually, in every case, when get a numerator needs to return a new instance, rather than for each of those places having new blah 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 blah, the iterators each implement a clone method, and then clone is used from that implementation. You can see dispose, the base implementation, is doing that whole setting state to -1 thing. This should all look super familiar if you watched the other video to the end. But because it is this base class, we can then very easily see in source.net all of the derivations, which accounts for all of the custom iterators we have. So if I click on this type in source.net and look on the left-hand side, each of those lines on the left-hand side of the screen, maybe I can make this a little bit bigger. Each of those is a custom implementation of one of these iterators.
Like 31 different derivations of iterator.
Yeah, exactly. The top number there. And so we were talking specifically about select, and you can see that there's about 7 custom implementations specific to select. And so if we actually went and looked at, probably easiest if I just click one of these and see where it's created from, we can see that inside select, we do the argument checking, right? I mentioned in the previous video that the public entry point itself isn't an iterator itself. It delegates and constructs things that might themselves be iterators. So we do some argument validation. We're doing a check here to see if the input is one of those custom iterator types that we just saw. And if it is, we ask that type, what select implementation would you like us to use? So it allows that implementation to choose. So for example, if that implementation is range, we saw in the previous video that if you did enumerable.range.select, you got a range select iterator. And so this is basically saying, hey, Mr. Range, I'm calling select, produce that range select iterator. But if it's not one of those things, then it's special casing these known, very, very common data types that exist in .NET. So it's looking for array, it's looking for list, And then sort of as a fallback, it's also looking for iList, which is super common.
So if I removed lines 31 through 49 and effectively backed up in time,
Yep.
then it would be using a standard IEnumerable select iterator. And effectively, I would be using a previous version of LINQ, a previous version of .NET, and it would still work. It would just be slower.
Yes. And if you had asked a question about how many of these things were around at the beginning, there were a few. So if you go back and if you look at the reference source for .NET Framework, which for LINQ basically hasn't changed since, I don't know, a decade ago or longer, there are a few custom implementations of iterators. But if I had to, I haven't looked recently, but if I had to remember, my guess is it's no more than 10. Maybe no more than 5. There were certain patterns that from the get-go were going to be super common. Where select, that's a super, super, super common pattern. And so from the get-go, that was special cased. As were sequences of select or where, where you get these, list of filters, where blah, where blah, where blah, where blah. Like those were all special cased. But a lot of these more intricate patterns were only special cased once it became clear that they were in fact common. And some of these special casings don't even show up here. There are other forms of special cases. So for example, I mentioned last time, I think, that if you have an order by, there are some pretty common things that someone does after an order by. For example, you might say .first. What you really mean is give me the min by whatever that predicate was. And so we will translate it into that operation and turn what was an order n log n sort into an order n search for the min. And there are various other customizations of that ilk. As most of these iterators, they all specialize for toArray, for toList, for element at, first, last. And so if you look at these iterator types, you'll see that this base iterator provides those virtual methods. And then each of those custom iterators overrides the behavior so that if you call where select toArray, you're getting an implementation of toArray that handles all of that in one fell swoop and doesn't have to call back through any previous calls.
All right. So returning back to the DOS prompt that showed us that we were within a couple of those are microseconds.
Yeah.
Of each other, we would need to. So if we wanted to compete with that, we're going to need to do some work, some custom work. What else can we do? It's already fast. What could we possibly do?
Well, we can certainly get this to match this, and we can do that by doing the same optimizations that are done in LINQ itself. Because LINQ is not magic, right? As all this stuff, it might seem like, oh my goodness, how is it possibly doing that? And then you actually understand how it's doing it, and then you can do it yourself. So we can achieve this difference by specializing for arrays.
Okay.
And we're not going to specialize for lists and for iLists and for all that stuff, but we can.
Right. We prove we can do it with one.
Exactly, and see what that actually looks like. So we can do this both with iterators, which we'll do first, and then we'll do our manual implementation. So let's go to our. Oh, that's not what I wanted. I wanted select compiler. So if we remember, this was our iterator-based implementation. We have our outside method that is doing the argument validation and is calling to our iterator, and then our, depending on how you count, 2 or 4 line iterator body. So if we wanted to specialize this for arrays, we would do something like this. We would copy and paste this, and I will rename this to enumerable impl. Put that there, and then I'll call this one array impl, right? And I will change this from tsource, from IEnumerable tsource to source. Now, interestingly, actually, let me come back to that. So then up here, I'll say if source is tsource array. So if we have an array, then rather than returning the enumerable impl, I'm going to return the array impl with array and selector. Now, even though I haven't rewritten the body of this method, this is already going to be almost as fast as the LINQ-based one. Not all the way as fast, but almost as fast. And the reason for that, interestingly, is because the C# compiler actually special cases for each loops over arrays. So if we, let me bring both of these.
Is it knowing that? I mean, we did a check on line 61 to say it's an array. Is simply doing that check enough to give the compiler a hint of what's going on downstream?
We already gave it that hint because I just strongly typed this as array.
I see. So by putting that as an array, that was the hint the compiler needed for line 78 to now turn into something special.
Exactly. So if we go and use something like SharpLab, which if you haven't played with it, it's an absolutely fabulous tool. And I just paste those two methods in here, and I forgot to do this.
And we haven't, I don't believe we showed SharpLab before, but there are tools like SharpLab that are valuable for folks to see so that they can get that interactive feeling of seeing code and then seeing the result of the code. Why would I use SharpLab over, something in VS? What does it provide?
I mean, it provides a live view as you type. You can see, what did I do? I just messed something up. There we go. It provides a live view of, as I type C# code on the left. On the right, I have my choice of seeing what IL this compiles down to. So it's basically live compiling what's on the left to what's on the right. Then I can also ask it to decompile that IL back into C#, so I can see a C# view of what IL the code on the left is producing, which allows me to see the kinds of lowerings and transforms that the C# compiler produces. One of my favorite parts of it is it also allows you to see the assembly code that you would get out of this. So it not only compiles it, but it then runs it through the JIT, to the just-in-time compiler, to produce IL. Now, there are a variety of reasons the IL may not be exactly what you would get if you did it locally, but it's often a good enough indication to kind of get a feel for what you wanted to find out. But in this case, I've got my my enumerable one and my array one, and I can already see, if I go down to my enumerable one, which is down here, we can see that we have, where is it? Enumerator. We can see there's an enumerator that the compiler has retrieved, right? This is exactly what we saw in the previous video. We had enumerator, and in the implementation of this, it's calling get enumerator. There's a little state machine here. It's calling, we saw almost this exact same code without the mangled names, right? We were calling selector, storing it into current, setting the state, returning true, and so on. But if we go up to the other version for array, you'll notice there's no enumerable or enumerator in sight here. So we're still for eaching over this array, but instead the compiler has just lifted out the iteration variable, and it's just going to be using an int I basically to go through the array.
So because a for each is just syntactic sugar over a for loop.
Exactly.
In the context of an array.
This code here is 100% equivalent to I equals 0, while I is less than source.length, I++.
And that's a good reminder to folks that, just as a generic concept, that's a good reminder to folks that might be looking at trying to outsmart the compiler and say, well, you shouldn't use for each all the time. It'll be okay. Trust me. You can use for each over an array. It's the same as a for loop. I think that as someone who started in C and then C++ in the 90s, when I was introduced to C#, I found myself thinking ahead and overthinking and saying, oh, I should make sure I use a for loop, not a for each loop, when I'm enumerating over an array. Right. This is exact proof that it's just not necessary. The compiler is almost always smarter than you are.
It's generally very good. And sometimes the framework itself is sort of not smarter than you, but has done more optimization than you have found time to do. It's an interesting balance, because on the one hand, we say, well, LINQ often has a bunch of overheads, right? You've got this this delegate that's going to be invoked on every iteration of the loop. So if you just did this as your own loop, you can avoid that overhead. And that's true. And there are certain circumstances where on hot paths, you really want to avoid using LINQ because it does add sort of unnecessary overhead. And if you can do just as well without it, you might as well do it without it. However, there are a lot of optimizations that show up that might actually, removing LINQ could end up being a de-optimization. So, for example, in .NET, I don't know, 5 or 6 maybe, or maybe 7, I don't remember, somewhere around there, we added optimizations into a bunch of the LINQ methods like average, sum, and so on, where if we can detect that the input is something that is a contiguous backing store, like or an array or a list of T, we can possibly use SIMD to vectorize the operation. So rather than doing the simple loop that someone might write to sum one number at a time, we might be able to sum 4 integers or 8 integers or 16 integers at a time, taking advantage of SIMD instructions. And so those LINQ methods will do that if possible. And so if you just remove all use of LINQ because you were told by Stephen that LINQ has overheads, you might actually be reducing the efficiency of your program by 4, 8, or 16x if you were using one of those operations. So to some extent, you kind of need to know where the optimizations are if you're trying to micro-optimize at that level.
Right. And to give people a little bit of historical context so they can understand what SIMD means and explain, like when you think about like x86 or the assembly language that I learned 20, 30 years ago, you're putting in a number into a register, you're doing a thing, and you do an operation to sum that number with another number. SIMD, S-I-M-D, is single instruction, multiple data, which is hardware support for doing an operation on multiple pieces of data in one instruction. What would have been dozens, hundreds, thousands of whatever can now be done on a computer with an acknowledgement, a formal acknowledgement that a computer now has multiple processing elements and not we're not just on one processor. We've got, 22, 32 processors.
Right.
Use all of the things available to you is what SIMD tells me.
And that usually amounts to, on today's hardware, that's typically instructions for processing 128 bits or 256 bits or 512 bits at a time. So if you're dealing with an int32, which is 32 bits, then if you have these instructions for doing 128 bits at a time, you can sum 4 integers at a time. So rather than looping through your array 1 by 1 by 1, you can loop through 4 by 4 by 4. Or if you had 256 bits, you could do 8 by 8 by 8. So we have the lower level support in .NET at varying levels of the stack for accessing all of that goodness the hardware has to offer. And wherever possible, we try and take advantage of it in the lower level libraries, such that when you use those operations, you just sort of implicitly get that SIMD goodness, and you don't have to go and use it yourself.
And is it the primary set of SIMD accelerated types in .NET is system.numerics?
There's certainly a lot there, but not limited to that. So pretty much every string operation that you can think of in .NET is accelerated in some fashion. Things like index of, sequence equal, any kind of comparison or memory copy operation, all of the operations like base 64 encode, decode, those are all now accelerated with these types. All the hashing support, like the XX hash functions and the CRC hash functions, those are all vectorized using the support. We shipped you mentioned numerics, we shipped a new library in .NET 8 called System Numerics Tensors, which includes a class called Tensor Primitives, which has on it, in the .NET 8 timeframe, and it had on it about 40 different operations that were all for doing various kind of mathy operations over floats, adding, subtracting, dividing, and whatnot. For .NET 9, we've extended that to be fully generic. So all those operations apply to more than just float. They apply to any of the numerical interfaces that are relevant. The things like iFloating point and iSigned integer and whatever else that shipped in .NET 7. But then we've also, I think, maybe tripled or quadrupled the number of distinct operations that are there. So there's POW and log, basically everything you can find on math and mathf, as well as on
Okay.
those generic interfaces show up there. And wherever possible, they are vectorized using these SIMD instructions.
Okay. So back to the work at hand here.
Very far afield.
No, that's good. I mean, tell us in the comments if this is what you want to see. But back to the work at hand. Line 78 now is just just a lowering or an expansion of what a for each was going to be. So you could Control Z your way to glory, as we like to say.
Yep.
So by simply strongly typing it as an array, we're getting a small benefit in perf there.
Exactly, and and again, not to go too far afield, but if you look at some of the analyzers that we add to various releases of the .NET SDK, a lot of them are geared towards sort of nudging developers in the direction of allowing things to be specified in a way where everything else just kind of works. There was an analyzer that was added in the .NET 8 SDK that will basically look at, let's say this was typed as IEnumerable, but it then looks at all the call sites and it says, hey, wait, you've typed this as IEnumerable, but all of your call sites are arrays. Just make this array. Just change this to be T-source array. Because then if the moment you do that, the code gen for this will improve. So you strongly type things and all of a sudden things get better. Or if you had a field that was an interface, you had a private iList whatever. Well, when you call methods on that, you're going to be doing dynamic dispatch. All your virtual methods are going to be virtual method calls. And best case is the JIT might be able to use something like dynamic PGO to devirtualize. But if you just remove the I and you just made it private list instead of private iList, there are no virtuals. So everything can just be direct function calls. The inlining just works. Things just get faster.
Yeah, you bring up a really good point. Again, we're going a little far afield, as you said, but it's worth noting that we have been slowly getting better in what the IDE does. That if you think Visual Studio or Visual Studio Code and tools like this are just pretty syntax highlighters, it's not just the compiler anymore. Historically, when squiggles started and a red squiggle was a thing, it was that's not going to compile.
Right.
And now we're getting into these more grammatical squiggles, these green ones and the blue ones, which are moving more towards formal code analysis in real time. And it cannot be overstated how that happened quietly and has been, as you said, gently nudging people towards doing the right thing. And then you also call that PGO, expanding that acronym, Profile Guided Optimization, new optimization technique for jitters that allows the JIT to go and say, this is how I think about it, is like, I've done this a couple times, I can do it better. And then just swapping it out while you're going.
The JIT generates some code, and when it generates the code, it sprinkles in some tracking, some instrumentation, such that it can then later go and say, what happened? Like, what was the most common type for this thing? How often was that code invoked? And then it can take that data and say, oh, I know what to do with that, and generate a brand new version of the code that optimizes for the patterns that it actually saw in practice.
Right. And those two things, the combination of really sophisticated analyzers, because nobody likes squiggles, and people are going to take advice when they see a squiggle, at code writing time, at compile time, and then PGO at runtime is giving people performance, for free. And a great deal of people worked on that to make those things possible. So, kudos to the team.
Awesome. So back to our main topic, because I keep taking us off. So what we talked about was, we've now done this for our iterator version, right? We've special cased arrays. Yep. And we were talking about, we wanted to do this for our customized version. This is what we'll do. We're going to copy all of our enumerable here. This is the implementation, the guts, the thing that replaced the actual iterator. So I'm just going to let me rename this to be, the name's fine. I'll just use a different name for the new one. I'm just going to copy and paste that. And I'm going to rename this one to be, let's say, select manual array. And now I'm going to go and just fix up a bunch of stuff, and we'll kind of work through all the squiggles. So we no longer want to have an enumerable as our source. Now we want this to be a T-source array. We're no longer going to have an enumerator. Instead, we're going to have an index.
Right, effectively pulling int I into this array.
Exactly.
Okay.
I now have some different types here, so we'll fix that up. We'll say this is an array. You can see that squiggly goes away. This should be manual array over here. That squiggle goes away. And now we're basically down. Oh, we don't need our dispose and our enumerator. That all remains the same. So now we're into our move next implementation.
Right. And we're moving next through an array that we know is an array, not running around managing state and thinking about move next in the enumerator context.
So we no longer need to call get enumerator, which also kind of means we don't even need multiple states here because all the states other than the ending one are kind of the same.
Well, is the state being managed by that private I now, really?
Oh, now you're jumping ahead.
Yeah, no, I'm just asking. I mean, I'm just along for the ride on these shows.
You got the punchline.
I'm sorry.
No, you're good. But we will get there. So right now, we still have two different things. We have a state and we have the I. So we're going to stick with that for just a moment. So I deleted the get enumerator. I no longer need this thing. Now the check for whether I have more work to do is just whether I is in range. So this is really if I is less than source.length.
Yeah.
Right. And then this just becomes source sub.
So yeah, source at I.
Right. And then you can see there's no more red over here on the left.
Hang on. Let me 1 second. Let me get us out of the way.
Oh yeah. We just talked about how we wouldn't need the right hand side at all.
So yeah, so you see that green line there. That's where all the squiggles are, and and people don't even think about that. They just kind of like let that happen. You've got green lines along the right and green lines along the left hand side as well.
Right. So this green line here is actually an indication of things that I've recently changed or recently saved,
and not yet saved.
Yeah, and then this is an indication. This is like a view of it, regardless of how big my file is. I can kind of see the whole thing.
Yeah, exactly. All right, I'll put us back over there.
So then the last thing that I need to go up and do is in my select manual implementation, we need to do the exact same trick that we did here. So I'll just copy and paste that in, and then this will just be select new, select manual array with array. So that's the core of our implementation. So let me go back up here. And we had talked about wanting to, let's just do that. So I'll just run the benchmark again.
Mm-hmm. Remembering that we were at like 4 microseconds and 1.3.
About 4.7 or so, and LINQ was at 1.4, maybe, something along those lines. And now we should see both the iterator-based one and the manual one get faster, because for the iterator-based one, I also added a fast path for array, and then for the manual one, we obviously just did so manually. So again, benchmark.net is kind of generating these customized implementations to test the different benchmarks. It's doing a very quick. I have a bug.
Well, it's good. Why do we have a bug?
I knew I had a bug because it paused.
But hang on though, don't lose it. Why do you have a bug? And let's talk about it rather than you quickly fixing it.
So I have a bug because, well, two things. One, and I know exactly what the bug is. I'll show you.
And how do you know it's there? The pause?
Yeah. So first, I know I had a thing because if you notice when we got up here, this line up here, this overhead jitting, this was basically just timing the first invocation, and then it would keep going. And then down here, when we got to the next benchmark, it just sat there. It paused, which meant that it wasn't progressing past that first run, which means it was hanging. It didn't make any progress. And I also then heard my fan turn on, which meant that the CPU was working super hard at something.
Now, why did it not hang forever?
Oh, because I stopped it.
Because you did stop it.
Because I control C. Controlled C to glory, I guess, is the version of
it's
that.
It's a new thing. We're going to make that a thing.
So the reason
is... I know why.
Yeah.
You never increased I. You never actually moved next.
I never actually moved next. So it was just doing the same iteration over and over. That would have taken quite a long time. Yeah, beautiful. All right, so we'll let that go again. Again, I have this set to be on this min run, which is why if you look in the error column, those error numbers are relatively large, because normally benchmark.net will run a lot of times to try and minimize the error, and it'll throw out the outliers and kind of give you a nice distribution. We can see I successfully started running faster.
Now we're
And
cooking.
it's almost done.
Benchmark.net just is a lovely, lovely thing.
It's so cool.
Such a wonderful service to the community.
Okay, so a few interesting things here. One, our compiler implementation did get faster. Our manual one got faster, but not quite as much, which means that I didn't do as good a job at lowering it as the compiler would have done.
Okay.
But I did get the allocation down to exactly what LINQ has. So that's a good starting point for us. So let me close that. Now, there are a few interesting things here. And we're going to try and basically optimize this. First, I mentioned that I don't really need this extra state, right? You jumped right to it. I now have two integer things that I'm able to track, and I don't really need both of them. I'm iterating through an array, which will have strictly less than int.max value elements, and as a result, the fact that I need an extra state here or there, I have room to just use the I as the state, or rather use the state as the index. So we're going to do a few things here. I'm going to get rid of this whole switch. I'm going to get rid of the extra I here. And I'm just going to use the state as the index.
That's interesting why you did that rather than deleting state and using I.
I did that because in here, I'm going to say I want to actually have something that I think of as I. And I'm just going to have I be 1 less than state, because state was initialized to 1, and I want to start off at 0, and I want to think of my iteration variable as I. So I'm going to transform my state to be an I.
Interesting. Why not just completely just yeet state and just I equals 0 and use I all the time?
If I come in, let me think about this. If I come into the method and, the state is initialized to 0 because our thread safety routine here.
That's right. And that's still required. We still need to be thread safe.
Right. Because we still have state that we're carrying forward. So I still want to differentiate between states 0 and non-zero. And so I'm going to use state to track that. And then I is just going to be, my iteration thing will just be 1 less than state. Now, then I need to do a few interesting things here. So I'm going to get rid of the underscore on this I.
Okay, it's not a private anymore. It's local and it's on the stack.
It's also not I that I really want to be incrementing here. It's now state.
Right, because you're not in the middle of a loop here. State is you just have I there just so you don't have to keep minusing 1 on it twice.
Right. Now, I'm also not doing anything interesting in my dispose. I was doing this enumerator.dispose before, but now I'm just saying, just set state to -1. So this catch block is kind of pointless.
Oh, I see. Because but that's implying that nothing could go wrong, and that the index in 131 is never going to.
This could still throw, and there is a. Okay, so I shouldn't say it's pointless. There is a behavior, an undefined behavior here, where what do you want to happen if you call move next and it throws an exception, and then someone reuses that object again? So that is it is undefined what should happen because you're not supposed to do that. If you get an exception out of move next, that object is basically
Well,
correct.
what's the old rule about exceptions is that they should only happen if they're exceptional, and you should only catch them if you can actually do something about it.
Right.
So
And you don't know what state this has been left in. If it
right,
throws an exception, who knows what state it's left in? So you're not
yeah,
supposed to use the object again. And
right.
as a
And
result,
before you needed to catch it because you knew that you could do something about it. You needed to dispose. Here, you're pretty much in huge trouble if this thing throws. So you might as well just cut bait.
I'm going to get rid of it. No, I could keep it, but just simplify things, get rid of it.
Sure, gotcha. All right.
Now, I do have a problem here, and that is if state were 0, which shouldn't be because someone shouldn't be calling move next on this thing, but they could call move next if they were to
Right,
cast.
and then
the
you're
object.
indexing on a -1.
So I don't want to do that. So I'm going to solve two birds with one stone. I don't want to kill them. I want to solve them.
Right. We don't kill birds. We solve birds.
We solve birds. We help birds. I'm going to help 2 birds with one stone. The other bird is this array here. Every time I access it, I'm potentially going kind of loading it from the class. That's not ideal for a few reasons. One, it's a little bit more expensive to kind of go back and get it. It's possible that the compiler had.
Oh, I see what you're saying. So you're saying you're going to access this property length multiple times, and
Right.
it's not going to change. You can hold that length somewhere in a. This really is low-level, thoughtful. Like you're really not over-optimizing. You're just regular optimizing. But I'm thinking to myself. No, but yeah, that's a good point. But then now I'm wondering if that's going to take up more memory if you're going to hold that at the class level or not.
Well, I already had it at the class level. It's not. Most likely the compiler was putting this into a register, so this is probably not helping with anything immediately, except because it's not guaranteed. If this was accessing source on the let me do what I was going to say first, and we'll get back to that. So the hyper optimization or micro optimization is I'm going to address both of my birds with one stone, help both of my birds with one stone, and I'm going to put this weird cast here. This is a little trick to say if I is negative,
right,
then it's going to wrap around, and there is no way that it will be less than source.length. Because source.length can't possibly be greater than int.max value.
That's why you said that about 5 minutes ago. You said that explicitly this can never be larger than int.max.
Right. So I'm now able to, I don't have to check whether I is negative because the check for inbounds is now handling it for me because I'm able to do it in one comparison.
Interesting. So you're not doing any if this and checking it. Like you could have 3 or 4 lines of code, but you've encapsulated it all on line 131 with that little trick. And it's not a less than check, it's an inbounds check. It's
an inbounds check, which I phrased it in a very specific way because on line 133, like one of the reasons we call C# a managed language is because there are all these services that are sort of provided for you behind the covers. The just-in-time compiler guarantees that if you index into an array and you walk off the end of or the beginning of the array, that it won't be walking off and stomping all over arbitrary memory. If you try and walk off the end, it will fail. And it does that by inserting bounds checks, extra branches into the code that says, what is the length of the array? What is the value you're indexing with? Make sure that one of those is less than the other, and only if it is do I allow you to index. Otherwise, I will throw an exception. However, we don't want to do that every single time we index into an array. So the JIT tries really hard to learn from the code whether that bounds check will be needed. And the JIT can see from this check that the value that I'm indexing into is now guaranteed to be in the bounds of the array. So it will then elide the bounds check that it would have otherwise injected here. So by doing this comparison, we not only eliminated the less than 0 check we would have had to add, but we also eliminated the hidden check that was showing up.
Right. A hidden tax, a couple of operations that you don't have to do, and in the middle of a tight loop, that's going to save you time.
Exactly. And so, this is now, and just because I can, I'll just move that there, just so that the last thing we do is assigning to current. Doesn't really matter, just for my own neuroses.
We all have those.
Yeah.
I'm all, like for a while, I used to be, instead of an I++ person, I'd be a plus I person.
Yeah. And so that's basically it. So now, we've got our manual implementation, and we should be good. So if we go, let's see, my ramble, my manual one. So if I go back up, just double check these are all still doing what I want them to do. Yeah. So if I now run this again, in theory, with any luck.
Well, we all know that your code runs exactly as it was written.
It runs exactly as it was written. That is a true statement. Whether it runs exactly as I intended, we will find out in a moment.
Well, what is it that they say? There may be an error between the chair and the keyboard. So we'll see if that's the case.
So
all right.
Kind of glancing at it, we can see our iterator was taking about whatever.
And you're doing this with a cold, which I think it's itself impressive. You're running yourself at like 70% optimal.
I woke up this morning with my head is just like totally full. I'm Dayquil'd up or whatever. So any errors, I'm gonna rack up to that.
Oh wow, look at that.
So now you can see that like those numbers are.
I bet you run that a couple of times and they're within, they're the correct. They are.
Yeah, I mean that's you really can't
statistically the same, because remember that microseconds are not nanoseconds. They are
right. And
millions per second.
This was for 1,000 iterations. So this is actually 1.4 nanoseconds per iteration. So they're differing by an inconsequential. I mean, I couldn't reproduce that level of difference if I tried.
That's awesome. Yeah. That's awesome. And then now back to popping off the stack to the beginning, and that's why you take a little bit of time and you do 7, 20, however many, 31 custom implementations. And what's nice about this is this means that I, as a user of LINQ, write my select, I write my query, I do it once, and then I upgrade to the latest version of .NET, or I take an update, and it's this thing just got faster.
Right, and even in .NET 9, we've done a lot of work in LINQ for .NET 9, so there are some new implementations there as well. We've optimized various things. I mentioned in the last video that we recently gathered some data on how LINQ was being used throughout NuGet assemblies in NuGet, and we used that to then influence. This is actually a more common pattern than we expected. Let's go make sure that works really well. There is, of course, a trade-off there. We could go and optimize every single possible pattern that we could think of, but that would end up significantly bloating the size of system.link in a variety of ways. One is, the more specialized implementations that we have, the more we have to maintain, the more likely it is that we have bugs. Excuse me. And in certain cases, we had that interesting discussion about undefined behavior, right? And I said, we don't need that try catch. Every once in a while, we find people actually depending on that undefined behavior. And then we have to make a judgment call as to, is this something that someone should legitimately be depending on? And in that try catch case, I'd argue no. But there are other cases where we've made changes and we back them out because we say to ourselves, actually, even though we wouldn't recommend doing that, it's legit. So for example, I mentioned that we specialize sequences of operations. So we have the ability to, for example, specialize enumerable.select.count. And we did at one point optimize that to be like, all right, well, if some code over here returned an enumerable that was created with select, and they return it out of a function, and then someone else doesn't care about it, they just want to call .count, they want to know how many things there are, we don't even need to run those selector delegates. We can just peer through it and just see how many elements are there. If it was array.select.count, just return array.length.
Makes sense.
And we did that. And then we got multiple people complaining that they were using count as a way to force the invocation of the processing of their query and were relying on the side effects of the select delegate from having been invoked.
I'm guilty of doing that.
So we broke you.
No, you're absolutely right, because you prep these LINQ queries and you get everything ready to go, and then you're like, okay, I need to like peek. I need to just kind of jump ahead and kick it a little bit to make it wake up. And the side effect of accessing a property kicked it.
Right.
Not a smart thing to do, but it was a thing. And then next thing you know, everyone does it.
And so there are a bunch of these cases where we're sort of, putting our finger in the wind and saying, like, is this something that, we would like to optimize this? Do we believe that this is something that someone could legitimately do? Could legitimately make a claim to saying, hey, that this is valid? And we'll avoid those optimizations if we believe that we would actually break someone. And in some cases, we've made, I think of 2 or 3 times where we've made such a change and we've had to back it out because we made the wrong call in terms of what people were actually doing.
In the interest of going off in the weeds for a second, we talked about SIMD, and we talked about how, there was a time before CPUs supported things like, SSE2 and different things like this. When you want .NET to run everywhere and you want it to run well everywhere, and then you start doing optimizations like this, are you guaranteed with this optimization that you just did that that's going to now be faster on my Raspberry Pi, on my Intel, on my AMD, on my new ARM chip that hasn't been invented yet?
So with this one, probably, but not with all of them. There are a bunch of things that legitimately differ in performance across operating systems and hardware, more hardware than operating systems. Especially, there are things that, actually, some very recent examples. We made a bunch of optimizations in regex, for example, that looked great on all the hardware we tested until we merged it. And then our regression suite started sending up red flares because for WASM in the browser, we tanked.
Which is now a target CPU type.
Fell off a cliff.
It's an abstract
so we had to go
and
back those out and then revisit how we could fix that before we could then eventually re-enable it.
Interesting. Is that so important of a CPU target? I mean, it is arguably niche, or at least emerging.
It's emerging, and if it was, we made these other platforms 10 times faster and we regressed that by 5%, we'd probably say, okay, it's debt. We'll figure out how to address that later. But this was like we made these 10 times better and we made that 100 times worse.
Oh, wow.
It was
massive.
That
makes sense. Yeah, that's valid.
Yeah.
That's valid.
So there are definitely differences, and they can be at any level of the stack. They could be in, the compiler. We're relying on some optimization that's in this runtime, but not that runtime, or relying on instructions to be fast on these instruction sets, but they don't exist over here. So we hit a fallback path and we do something else. There are many different things that can impact this.
Okay, so let me ask you this. We're 50 minutes into LINQ Part 2. Do you think, right now we have a great implementation of select.
Yeah.
But could we, in the time we have, maybe in the next 30 to 40 minutes, add a where? So we could do a where select?
We could.
You want to give it a try?
Yeah. I want to say one more thing before we do, and that is I was mentioning, reasons why we wouldn't add a whole bunch of different implementations. And there's a very current reason that is, that weighs on us every time we think about adding a new one of these. And that has to do with native AOT. And that if you're using a JIT compiler, you're only compiling to assembly code the things that you actually use. Mm-hmm. So if I call enumerable.select with an array, but there are 8 other implementations for different data types, and I never touch those code paths, I'm never going to go and generate.
Yeah, they may have come along for the ride if you didn't trim them off and remove them, but they're just sitting around as a resource that is uncompiled.
As IL that we haven't yet turned into assembly code. Mm-hmm. With native AOT, and ahead of time compilation, we have to generate all possible code ahead of time that we might need. And at that point, we don't know whether we're going to need the code for array or for list or for range or for whatever. So we have to generate the code for all of them. Now we know if there's a method A we can see whether method A is called at all. So if method A is never called, but method B is called, we can trim method A away and we never have to generate the code for it. We only have to generate the code for B. But if you have a method A that calls a whole bunch of different methods based on type testing the input to A, we don't know what that input was because we have to keep A, we have to keep all of those other implementations. We don't know which of them are actually going to be needed, so we have to keep them all. We refer to that entry point method as a choke point because everything goes through it. And so if you route everything to it and then it splits off into a whole bunch of things, you have to keep all of that stuff, even if it may not end up being necessary.
Okay, so then why would not, and this is an ignorant question, but why would not tree trimming and dead code removal not be required in an AOT compilation scenario if that is the
concern? It is, but it can't see everything. So it could see whether A was called, but it can't necessarily see through every possible code path that could possibly reach A. Is the input to A going to be arrays versus lists versus ranges versus whatever? And so unless it can actually figure that out and pass that information into the trimming of A, it's in the A implementation, it ends up having to basically keep all of the implementations that A references. And so from a trimming perspective, these optimizations in LINQ are kind of the devil. And we have to do this balance between how big your assembly might end up being because it's keeping all this code versus how fast might it run at execution time. So there's this constant balance we're thinking about.
All right.
Anyhow,
cool.
You were asking about where.
Yeah, let's see if we can maybe take it to the next level if that's okay.
Yeah. So I'm not going to go and do a whole bunch of different variations of this.
Yeah, of course.
Let's just focus on arrays.
Let's also just reset and let's go and open up some compiler, some manual, and just remind ourselves what LINQ we're actually doing.
All right. So
the actual benchmarks.
Oh, the actual benchmarks.
Let's just see the usage. Let's just go up the stack a little bit, and open up line 15 there. There you go. Okay, so we've got some selects here. Select manual. Select So enumerable dot select.
Yep.
And we want to go and do a where. We might say where.
Right. So now I can either write this out using explicit static method syntax, which would be like enumerable.
Which we haven't actually talked about the implicit. We haven't talked about the non-static, style of LINQ, the I part of LINQ integrated.
Right. So I could do something like this. I could do something like this. Those two lines are identical. It's just whether I used extension method syntax or explicit static method syntax. Or I could do what you were just suggesting, and I can have something like in source where true, maybe true is a bad example, but select I times 2, and then I could say for each int I in values. So that is this is the integrated part.
I've always loved that. I just I don't think enough people use that. I just think it's just makes me happy. I don't know why.
I like the syntax highlight. It seems like the integrated part sort of feels warm and cozy.
It's very comfy. It's very comfy.
So these are functionally all the same.
Okay.
So we want to be able to do. Actually, let's just use this one just to keep it consistent with what we'll do for the manual. So we want to implement a where for our manual one as well.
And our source, remind me what our source is doing. It's a range of 1,000, maybe.
Our source is a range from 0 to 1,000. Yep.
So here we're projecting that range, and we're getting numbers from 0 to 1,000, and then doubling them.
Right, and I think I said I here is true. So maybe we'll just pick the even numbers.
Yeah, there you go. I was just going to suggest something like that. So we're going to double them and get evens.
Right. So we'll do this by, let's just do enumerables because it'll keep it easy. I won't worry about that array specialization. So to make this easy on myself, actually, let's write the iterator code first because that'll allow us to see easily what we're trying to accomplish. So let me just delete the array code here, and I'll delete it in my manual one as well, just to keep it clean, and get rid of this guy. Okay. So I want to copy this select compiler, and we'll call this where compiler. Now the signature for where, there's no separate T result. It's just filtering T source inputs and producing T source outputs. And then instead of it being T source selector with a bool, with a T result, it's a T source comes in and it's true false whether to include it or not. So we'll call that filter. And this will be filter, this will be bool, this will be T source.
I think your line 71 T rebools, you got a bool inside of a T result there.
There we go. Bad copy paste.
Okay.
And then the semantics here are instead if filter item yield return item. So again, with iterators, most LINQ functionality, with the exception of some of the harder APIs like group by or join or those, most of them can be trivially implemented with an iterator, kind of how you would express it. For each item, if it matches the filter, include it, right? And that's exactly how it ends up being written out.
This is almost impossibly simple, though.
Yeah. And you can even make it shorter if we don't care about style.
You were going so fast, and it's like, yep. Like, but at the same time, it's like, yeah, you pass in a func, takes a source, returns a bool, you make your decision, and then on line 74, whatever they chose to pass in, which potentially could be, a check that's expensive, I suppose, if they made if their expensive check, I don't know, broke the law of Demeter or dug into an object or had some secondary side effect, but this is clean and fast.
Yeah, and from a perf perspective, in general, it's good enough. And in places where we can make it faster under the covers, we will. It's only in like the hyper optimized consumers that you would care to say, I don't want to use it.
So if you scroll up a smidge to that lovely integrated stuff with the syntax highlighting that we love so much.
Oh, I think I deleted it, but I can put it back.
Sorry.
IEnumerable int values from I in source.
So in this episode, in our previous episode, it's clear when you are calling enumerable.where or you're calling whatever dot some link, I can tell it's like, oh, that's the one Stephen wrote earlier. But how does the compiler know, like on line 42, that the where that implicitly is said there is my where?
So in this case, these contextual keywords in the C# compiler expand to sort of a known pattern. And they're just saying this where is going to look for a certain method off of this. That's a certain pattern of where. And so whatever this is, doesn't matter what type it is, it's going to look for something with that appropriate shape. And this is why in part one, I guess, we said, LINQ is different things to different people. LINQ is really a specification for those method shapes, but there's an implementation of it built in for IEnumerable. There's an implementation for IQueryable. There's an implementation for IObservable. There's an implementation in EF and an entity framework. There's an implementation here, an implementation there, and all that is just the right shape with certain parameters being defined to be the relevant type that would show up in.
Well, now, when you say the right shape, in a strongly typed language, in a language like this, it's usually an interface. You have to implement that interface. But then you said shape, which makes me think about like duck typing, which is like, well, it kind of looks like a duck.
Typing. This is it walks like a duck, it quacks like a duck, it is a duck.
Yeah.
It has a filter. It wants a filter. It is where, or whatever the right analogy would
so
be.
If I had some custom types, if I'm doing something fancy, something scientific, something obscure, I can still use this format on line 41.
Yep.
And
You just
have,
need to
as long as my
provide-
where is shaped correctly, I get the beautiful syntax, and it's going to call my implementation.
Yep, there's a set of, as long as, for this, I would basically need the right, provide the right overload for where over my particular type, and the right overload for, I guess, select many. I think this would actually compile down to maybe select one of those two.
Yeah.
Well, we can even see. So we can just look. Let's go back to, I said Sharp Lab is really
Yeah,
useful.
I was hoping you'd come back over here and
so
show,
let's just
show us that very
call
thing.
this foo. Let's do something else, example. And if I here just do return this.
Yeah, and you have to add using LINQ.
Using system.link. Per second. Oh, right. This is not going to work. We'll just do true. Doesn't matter right now.
Yeah.
Star can be to source. Of course, we'll just select I.
It's giving you a hard time, man.
This is T results. This should be int. And it doesn't matter. Do int int.
There we go.
So there's where. Oh, there's just where because all I selected was I. So now that I have this again, let's put it back the way it was. 2 equals 0.
Evens. Get all the evens.
Yeah. So it is select, not select many. I know I was thinking select many. So it's a little hard to see.
Yeah, I can see enumerable.select, enumerable.where, which is literally what you were writing before when I asked you to go back and expand it into this syntactic sugar format.
Well, for the select many that I was thinking, I believe if I did this, if I did from j in source, where I equals mod 2, select I times j. Now...
There's your many. You passed it.
Did I pass it?
Right there.
Yeah, here it is. Yeah.
Select where, select many.
Yeah.
The first one's the select. Nice.
So, this is fun. You can kind of see what it compiles down to.
Cool. All right. So do you think that your where is correct that you wrote in 2 seconds?
For this one, yes, I believe this is correct. But let's test it. So I can come back up here and we'll do that similar kind of smoke test we did before. We'll just do console.writeLine. And I had, let me grab this. So we have a source, and we'll do console.writeLine enumerable dot. We do source enumerable dot select on enumerable dot where with our source, and we were doing I mod 2 equals 0.
And that's their where, not your where, right?
This is the built-in one.
Right.
And then here we'll do tests.select compiler, tests.where compiler, and we run that.
That's your implementation.
Right. Build, we get the same.
Look at that.
We haven't done all tests, but a quick test suggested there.
Ship it, baby.
Exactly. There's no possibility, no problem.
No chance. The fan didn't turn on. It must be fine.
We're good. So now we want to go and do the same thing as this, but with our manual implementation. And this starts to feel very rote, which also highlights why we have that base iterator type in the actual LINQ, because a lot of it can just be factored out. So let me, again, we'll take my select manual enumerable here, and I'll make this where no longer has a T result, no longer has a T result, no longer has a T result. This is just source.
Now, are you... Okay, so you copied where manual enumerable and select, because where manual enumerable is
I changed the wrong one.
It's currently collapsed.
Oh, I meant to change this one. I changed...
There you go.
Yeah, I just copy and pasted this to this.
Yeah.
And now I was changing this. So,
and I noticed that you're not doing it as any kind of scoped refactor. You're doing it all manually just to make sure that you're being explicit and you're not getting any side effects.
And just to kind of show what I'm doing.
Yeah. Too much magic otherwise.
Exactly. So, and again, most of the stuff is just, it's very clear what it needs to become. I just eliminate the squiggles.
Yep.
This goes away. This becomes bool. This gets changed to filter. Let's rename this to filter. I don't know if I that. There we go. This is T source. Most of the actual logic remains the same. This becomes that. This becomes that with filter. And I don't have to change anything to do with states or anything like that at this point. Mm-hmm. This is T source. We can see the red disappearing from here. And now we're down to our move next method.
Mm-hmm.
Now our initial case is the same, right? We call get enumerator. We go to case 2. Now we start to differ a little bit though. So we need here to say if filter on enumerator.current, then we want to return true, and this we need to not select something over the item, but we want to store it into current. Now, this is a problem. The fact that I have 2 of these here now.
Yep.
So I'm actually making 2 interface calls to enumerator.current. There's 2 possible problems here. One, there's a perf issue. I'm making 2 interface calls. That's not ideal. Second is I'm actually not guaranteed what this current property is doing. It really should be idempotent. It really should give me the same answer each time. But I don't actually know what this interface implementation is doing.
Are you concerned? Are there a lot of chances that there's some side effect on a property get?
You would be surprised what people do, or maybe you wouldn't. But there's no good reason for us to make 2 calls into it. We might as well avoid it. So I'm just going to come up here and I'm going to have a little property called current, or a local called current, and then I'll just use that local multiple times. And this way I both avoid any possibility of side effects.
Well, whatever side effect happened, it only happened once.
Exactly, which would be what was expected.
Yeah.
And I also avoid the overhead of multiple calls, which could be just the interface dispatch, but it could also be if this property was doing a bunch of allocation or whatever, I can avoid that. However, because of this filter, and I'm checking this filter, this if is now wrong. If you remember in our initial implementation,
well, it's not. Yeah, it's whose responsibility is it to move next? Like, what does move next mean in this context?
Well, the initial thing here was a for each loop, but I wasn't actually yielding on every iteration. I was only yielding if the current thing matched. So I can't rely on calling back into this to push me next. This needs to become a while.
Yeah, right. And you could spend a very long period of time in that while loop.
You could, if you had, if you had 1 million elements in your enumerable and only 3 of them match the filter, you could be in a tight loop here, just looping through each of the elements, and it would be only once you actually evaluated this and then returned out of here that you'd break out, and then the next call in would re-enter the loop. So that should be it. We don't have any more squigglies. We don't have any more red showing up. If I go back up to the top here, and I do select manual. Oh, I think maybe when I copied this, I didn't add a where manual. So let me also, did I? No. So let me copy this, and I need to say where manual that uses where manual, and this will be bool with filter. And this is that.
What is it mad about? Oh, it's mad about that enumerator T source.
Enumerator.
The second interface at the end of line 178.
178. It's not about
enumerator T source.
Here. This should be this right there. Yeah.
All right.
Thank you. So now I've got select manual and where manual, and with any, what did I do? Where manual. Oh, that still has.
See, I was saying on the line at the end of that line. Yeah, there we go. Cool.
And now when we run it, we get the same value for all of them, which is what we were hoping for. It's what we were expecting.
Dig it.
Now, the interesting thing that we saw when we were looking at these specializations in select and so on is that it wasn't just specializing for specific data types like T array or list of T. It was actually optimizing for information being passed between LINQ operators. So where followed by select is so common that we want to treat that as something that we really can optimize for.
Interesting, because I was thinking about this kind of Cartesian product of all the different things potentially, but you're really just acknowledging the fact that the 80-20 rule indicates that where select happens way more often than all the other combinations.
Exactly. There's some that are just way more important than others. And just as a kind of a quick glimpse into how that actually works is, let's just go down here and we're going to copy our select implementation one more time. So let's copy this and we'll paste it down here. And we're going to name this one to be where select. So it's still taking in a source and returning a different result. But in addition to having this selector, we're also going to have a filter. So we're going to have both.
Right.
And we're going to basically treat this as the combination of both a where and a select. So when you call where and then you call select on it, rather than generating just a dedicated select that will iterate through the previous where, well, we're going to grab the filter out of the where and include it with the selector in this brand new iterator that we create here.
Would this then be so common and so often that now this is a shape that needs to be recognized by the compiler?
It could be. That starts to put a whole lot of specialization into the language itself. So it hasn't really gone there. There's no where select.
That's kind of my question. Like, I've got to where, I've got to select. Like, if it happens so often, how are you going to notice it and then get people into this implementation?
So we can notice it. We'll see how we notice it.
Okay.
In terms of which we choose to optimize, we rely on static data sources. Querying, looking at calling patterns in something like NuGet, all the assemblies there, and seeing that this pattern emerges as a super common thing.
Cool.
Interestingly, this where select is one of the ones that has been there since the very beginning of LINQ.
So this was identified early on. It's like, this is going to happen all the time. We should implement this. I just want to understand how, like, I've never been calling where select, enumerable.where select. So I'm trying to figure out what's the path as the user higher up that gets me down here. So I'm looking forward to seeing that.
Yeah. So the way that it would show up in the code that you wrote, you probably wouldn't write it in this form. You'd write it in this form. You'd write source.where .select.
Right, exactly. So then that dot select. Well, but that's two functions.
It's two functions, but we're going to turn it into a single iterator.
Okay, dig it.
So in terms of what you actually process.
Right.
So let's go back down here. So now this where select iterator has both the selector and the filter. So we're going to need to include a few more pieces of information here. So we're going to have our filter, this bool, and this will be filter. And then we'll store our filter as well. So this will be filter, and this needs to be where select. A lot of this other stuff remains the same. You are unhappy because, it's the wrong type. That's why you're unhappy. Where select, there's no argument. Right, this also needs filter. You gotta love good compiler errors. Okay. So again, there's all this boilerplate that we kind of breezed through, and that a lot of that boilerplate in the actual LINQ is pushed down to that base iterator method. So all we really need to focus on is our move next. So we're going to make basically the same changes that we saw for the previous round. I'm going to change this to an enumerator, to a while loop from the if, rather. Mm-hmm. I'm going to have my current item here be enumerator.current. And we'll do our filter on current. And we'll pass current here. So now this single move next method encompasses both the filter for where and the selector for select in one loop. We're not the only place we're calling out to a previous thing here is whatever enumerator this was actually wrapping. So we're going to go back up. You asked, how does this actually flow through? Mm-hmm. We're going to go up to our select manual now. And in here, I can say if source is where manual. So I can actually now type test to see whether this is the custom enumerable that was returned. and this is like the key reason, some of the micro optimizations we do in iterators are nice, but this being able to look at the actual type of the previous operator and extract information from it is the key secret ingredient.
And that's the question I was asking. How could you possibly know and then shift me down? That was the moment right there.
That's the one. So I'm going to change both of these two pieces of data that I need to pull out to be internal. I need to know what the where was operating on, and I need to know what its filter was. Because up here, I'm going to say return new where select manual enumerable of t source t result. The actual source here is whatever the source of the where was. So if you had a foobar that you called where on and then select, this where select iterator needs to process the foobar. We're going to pass in the filter from the where, and then we're going to pass in our selector. And so now when you call this, foobar.where.select, this will be the only iterator that's relevant. The where iterator that was created as an intermediate step will be thrown away. It's dropped. It's not referenced anywhere. And the only thing that's doing processing will be this method, which had this move next that was doing both the filter and the select. And with any luck, if we run this.
Okay. And while you're doing that, just as a reminder to make sure that I understand, and folks who may not be doing internal a lot, you might find yourself doing private and public and protected, but internal means accessible within the same assembly.
Exactly. Yep.
Okay. Which is, you wanted to make it available, but not available.
I didn't want to expose it. I don't want anyone to know about this where select iterator, other than if they print out the type and happen to see it. But it's an implementation detail that we're doing under the covers as an optimization. And we see that all of our select manual implementation, even though this was customized, we're still getting the same answer. And of course, if we drop the sum here and see what the actual types are that are involved, we can see we got our where select manual enumerator. That was this custom thing that we had created. Whereas for the iterator one, where we were just using the iterator directly, it has no knowledge of what came before it. It was just doing its normal loop. And we can see that indeed LINQ itself was specializing for the combination
with
of
their own where select array. So you have a where select enumerable. You could go and make a where select array or where select this, where select that, all based on your efforts and your analysis of whether or not it would help the customer.
Exactly. And you can see in LINQ itself, if I look for what iterators there are and we go down to where, we can see there is an array where iterator, a list where iterator, array where select iterator. Yeah. These names are slightly different than the ones we're seeing in the code because I'm running with .NET 8 and this source code is for .NET 9, and we renamed some of these internal types of the intro. But yeah, and that's what LINQ is. LINQ is this set of simple operations that you can implement with iterators. And then in some cases, we choose to do the more complicated thing and specialize their implementation for performance. And it's very fluid in terms of what we optimize for, how we optimize it. We generally don't take optimizations away unless they were breaking someone, but we do add in pretty much every release, there's more and more patterns that get recognized in one way, shape, or form based on what we see people actually doing.
Very cool. Well, this has been fantastic. 2 parts, roughly 2.5, 3 hours.
Sorry.
No, hey, dude, this is like 8 hours of content in 2.5 hours. If you just made it this far, I don't know if you somehow just showed up an hour and 20 minutes into type part 2, make sure you watch part 1. We started on a blank sheet of paper, implemented select in a couple lines of code, started to slowly build, running benchmarks, confirming that we got it to work. We made it right. We made it fast. And then in part 2, we went from adding a select, adding a projection, to adding where. And then again, make it correct, make it fast. And now we've got a path to go and do this on ourselves. But even if we never do this, even if you never write LINQ from scratch or even write a custom iterator, you know now how to drive stick shift if you needed to. And now you can enjoy the benefits of driving an automatic shift car and using LINQ happily, knowing now what is underneath it.
Exactly. And
Fantastic.
that's really it. I don't want people doing this unless they actually find a strong need to do it on their own. But
Mhm.
just knowing that, oh, hey, I have an array here, or if I'm choosing between a queue and an array, which one's going to work better, or why did it get faster all of a sudden when I changed the type? This is why. And having that
Fantastic.
extra information is just knowledge is power.
All right. Well, we have declared this is now called deep.net.
Okay.
Folks have enjoyed, hopefully, our LINQ Part 1. This is now LINQ Part 2. Be sure to check out our await and async video, and we'll have a regular expressions one coming up soon. And we got a whole bunch of cool stuff in the pipeline. If you like it, please like and subscribe, share with your friends, and big thanks to Stephen Toub for spending so much time with us.